Okay, guys, it's 9 a.m. exactly, and we can continue. All right, so exactly 1 week left. So the last class is going to be in a week on Thursday, right? Okay, but we still have some material to discuss. So today we're going to discuss interference of light. Basically, we already introduced conditions for constructive and destructive interference in our recitation class. Some of you in 2 recitation classes, you know, you're going to do it today, right, after this lecture. So for you, it will be slightly ahead, but it still should work. All right, and we haven't solved many problems, right? At least in my recitation class, I only started discussing problems, so we're going to do it on Monday. And as a result, this current homework will be postponed, right? I will inform you. It will not be due Sunday. It will be due maybe Tuesday or Wednesday. I will think over that and send over the weekend. No, today I will think, and I will inform you about that tonight. Okay, so first, let's refresh what we discussed recently in order to connect with today's material, right? Okay, so it's chapter 33, right? And so in the recent recitation classes, first of all, we introduced a traveling wave. So that is the equation of a traveling wave, right? And also, again, as I said in the previous recitation class, we discussed interference of 2 traveling waves, and we ended up with this condition. So if you calculate this 2 pi over lambda times the path length difference plus the inherent phase difference, and if that is equal to integer number, m is an integer, not math, it's an integer, 0, 1, 2, 3. So if this is equal to integer number of 2 pi's, so then at that point, you're going to have or observe constructive interference. If that is equal to m plus 1 over 2 times 2 pi, then these are conditions for destructive interference. We derived this, right, in our recitation classes. And then, of course, we adjusted this for 2-dimensional waves, for example, circular waves, because again, this was derived for a wave propagating along a straight line, 1-dimensional wave. And then at the end of the class, we made a switch to 2-dimensional waves, circular waves, and also it can be applied for a spherical wave, right? But we discussed circular waves. All right, and an equation describing circular wave is this. It's basically exactly the same like for 1-dimensional traveling wave, but you just need to replace x with r. Right, you see, x with r. And as a result, using this equation, you can describe circular waves. Basically, how can you create them? Let's assume that you have a pond or lake, and if you start creating waves somewhere in the middle of that lake, of course you will create these ripples spreading out, right? Sort of in the form of circles. So how can we draw those waves on the picture? We draw using circles like this. Again, we discussed that in our recitation class. And these circles, we call them wave fronts, wave front, right? So it is a collection of crests. Again, you can easily imagine when ripples get spread. So you can see circles which are created by crests, and also there are circles created by troughs. It makes more sense to use crests to visualize 2-dimensional waves. So you see, all right. So at the point where this line, we see a crest. You see a crest. Then next wave front. Again, crest. If you draw another wavefront, again, there will be a crest over there. And of course, between these 2 wavefronts, we have troughs, right? So over here, at any point between wavefronts, we have troughs. Then, basically, what is that? It's a snapshot graph. It's a snapshot graph. It's just basically a picture of a circular wave taken with a camera. And in the snapshot graph, what's the distance between crests? It's a wavelength. So the distance between these circles, wavelengths. Of course, if you draw another wavefront over here, again, there will be lambda, 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 and lambda. So every time this distance between wavefronts equals to the wavelength. Right. Okay, so we introduced these circular waves, right? And then we adjusted this condition for circular waves. Right, again, these waves must be identical. It means, what do I mean by identical? They must have exactly the same amplitude. Then they must behave in exactly the same way, in the same way in space. It means wavelengths must be the same, and they must behave in exactly the same way in time. So the period must be the same, right? So if waves identical, yeah, we can apply these conditions for circular waves. Again, conditions exactly the same, just you need to replace x with r. So condition is 2 pi over lambda times the path length difference. Path length difference is just an additional path that the second wave must to cover relative to the first wave on the way to the point which you analyze, right? And plus inherent phase difference, and of course, if it is equal to integer number of 2 pi, it's a constructive interference. If it's equal to this, destructive interference. Basically, we will have to apply this now for light. Right. Okay, and before we start discussing that situation, let's also look at the very special situation. What if two sources producing these waves are identical or in phase? In that case, the inherent phase difference is 0. Basically, it's sort of like what if you have two sources and look at the initial moment of time and take a snapshot graph and draw a snapshot graph. You will see basically that the first source produces sine function. And if you look at the second source, it will also produce sine function. So basically, they produce exactly the same waves. In this case, we can say sources are identical or in phase, and the inherent phase difference is 0. Again, we discussed it in our recitation classes, right? So in this case, if inherent phase difference is 0, so that will be 0, and as a result, this condition can be simplified. So if this is 0, then 2 pi over here and 2 pi over there can be cancelled. Only m will be left, and this lambda can be moved to there. As a result, condition will be much simpler for constructive interference. The path length difference must be equal to m lambda. We're going to use it today, right? And then, of course, a similar way, we can write conditions, simplified condition for a destructive interference. Again, delta phi is equal 0, so 2 pi gets cancelled, and delta r will be equal to m plus 1 over 2 times lambda. So constructive and destructive interference. So these we're going to use today. Right. Okay, so after this sort of introduction, in order to connect what we're going to discuss today with our recent past, now let's dive in a light interference. Okay, now I feel like we are more or less ready to do that. Okay, so first, models of light. How do we, okay, researchers, engineers, right, model light? Everything that we do here, it's our way of modeling stuff which God created, right? Okay, so that's how we model. Okay, so there are two ways of modeling light. If let's say you have a wavelength of this size, light with the wavelengths of this size, right? And let's say this light is interacting in your experiment, in your observation, with an object, and the size of the object and the wavelengths are comparable, right? Comparable. It doesn't mean exactly the same, just comparable. Lambda is sort of similar to the size of the object. In this case, when they interact, there will be lots of wave phenomena around an object, like a diffraction and stuff like this, which you can describe only if you treat light as a wave. And you have to use what is called wave optics, and that's what we've been doing now, right? So if lambda and wavelengths and the size of the objects are comparable, then wave optics must be applied. Look, for example, it's easier to visualize using waves of water or water waves. Look, we have a here opening, small opening of size L. Here we have a water waves hitting this opening, right? And you see there plane waves. You see the wave fronts are parallel to each other, and they're basically straight lines. And you see the this is the wave front, this is the wave front. The distance between them is lambda. And you see the wavelengths and the size of the object basically comparable. And as a result, after this opening creates basically circular waves. It's a basically diffraction effect. And in order to describe it, of course, you have to treat this as waves, right? And the same happens with light. Okay, so that is wave optics. Now let's look at the next situation. What if the wavelength of light, it's like the light which we use, okay, visible light. The wavelength is teeny tiny, very, very small. And if you want to describe interactions of this light, for example, with this flipper, clicker, whatever it is, this is, of course, there is no point of treating light as a wave, because the size of the wavelength is much, 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 much smaller than the size of this object. In this case, it's much easier and much better, and still you can describe what you observe if you treat light as a ray and use ray optics. Maybe at the end, in the last lecture of of this semester, we're going to discuss ray optics. We will see how fast we move. Right? So if the wavelength of light is much, much smaller than the size of the object, then of course there is no point of treating light as a wave. No, you can use what is called the ray model, right? Geometrical optics, ray optics, and that's what we usually use to describe our just a regular light. Okay, so but today we're going to discuss this situation when the size of the object and the wavelengths are comparable, and we have to use wave optics, right? Okay, so now after sort of presenting this, now finally we can start discussing what is called double-slit experiment. It was done first, okay, it's 1801, it's before Napoleon Wars in Europe, by Thomas Young. So he showed this. So what did he observe? So let's assume that we have, okay, I took this picture from the book. So let's assume that we have this screen with two slits, small openings, right? This slit number 1 and slit number 2. And let's assume that we illuminate these slits with a laser light. It's very important to use laser, monochromatic source. If you use just a regular light, right, from the bulbs, right, no, you're not going to observe what we're going to discuss. Right, and so the size of the slits, since the size of the slits, you see this L, is comparable to the wavelength, then as a result, like in the previous slide we saw, there will be diffraction over here, and after this slit, after this opening, or we can say this slit, will create sort of like a circular wave, right, after the slit. You see this picture, right? So we have this bunch of wave fronts created by this slit. Of course, strictly speaking, it will be spherical wave, but let's assume two-dimensional situation, and we are going to talk about circular waves, right? So we're going to see these circular waves, observe. Then the second slit is going to do exactly the same. It's going to create the second circular wave. And of course, these two circular waves, which basically exactly the same, because what? At this point, we just split our laser light into two. So this wave, this circular wave, and that circular wave, they're basically identical. They have the same wavelength. I mean, yeah, let me start with amplitude. They have the same amplitude, then the same wavelengths, and the same period. Two identical waves, of course, they are going to interfere. So all that stuff which we derived in our previous recitation class and which I refreshed just now can be applied here. Right? So now let me let's look at this situation from the top. It will be easier to see. Right? So again, it's exactly the same, but just top view. Again, you see we have two slits, this, right? So this is laser light hitting, right? And then we have this circular wave and this circular wave. And you see they're going to interfere in that region. Interfere, giving us bright and dark spots. Pretty much this whole field will be filled with dark and bright spots. And if I ask you, can we, for example, take any point over here and can we come up with a conclusion? Are we going to have constructive or destructive interference at that point? Of course, we should be able to do it now. That's what, okay, at least in my recitation classes, I started discussing at the end of the class. We haven't calculated, but I discussed with you, with some of you, right, the idea. So yeah, exactly the same, right? So find the inherent phase difference, then measure R1, measure R2, subtract them, use those conditions which we discussed, and you will be able to come up with a conclusion. Are you going to have constructive or destructive interference? Basically, from the physics point of view, there is nothing new for us. It's just the nature of the waves are different. Nature of the wave is different. Now we're dealing with light. So what's new in this, in today's lecture? Because as I said, basically physics is exactly the same. And the new is this. So the problem with this setup, yeah, we know that this area will be filled with bright and dark spots. But for us, because usually it's done in air, in a room filled with air, or maybe vacuum, it depends on your experimental setup. Pretty much, we cannot see these bright and dark spots. They're just basically invisible for us. Usually, during the normal semester, for this class, I bring demonstrations, right? I bring laser, a double slit, and project and show the bright spots and dark spots on the screen. So you can see, everything can be, okay, you can see that you cannot see the bright and dark spots. And that's the problem, right? So if you want, for example, use this system, for example, to measure the wavelengths of the laser, it will be complicated to use. So now we need to somehow get over this problem. And the easiest solution, what if we just take a white screen and position it over here? You see, position over here the white screen, and as a result, we can see all those, okay, not all, but bright and dark spots produced where the screen is. So from point of view of people who work in optical lab, from the point of view experimentalists, right, engineers, right, of course everyone would do something like this. Put a screen in order to observe these bright and dark spots. So now the question is, we just need to adjust, slightly change those conditions which we derived and which I reviewed just a couple of slides ago, adjust them for the case of the screen. So we can, for example, measure the distance on the screen, for example, and so we can tell that, let's say, 5 centimeters from the center of the screen, we're going to have bright spot or dark spot. So basically, the whole idea of today's class, we need to adjust those conditions for constructive and destructive interference for the case when we see bright and dark spots on the screen. That's it. So basically, we just need to derive the formula which an experimentalist can use in order to predict where is he going to see bright and dark spots on the screen. That's only new. Okay, so here let me open the idea. What I just told you is I typed over there. Because physics is exactly the same like what we discussed in the recitation class, in the previous recitation class. Okay, so now let's get into this adjustment. We will massage those conditions in order to get what we want. Okay, now there will be some geometry. So guys, if you try to write following me, it will be difficult for you, right? So all these slides I already posted in the Blackboard, right? So, and at the end of the day, we will just use the final formula only, right? And again, I don't feel like just giving you that formula, because everyone who is in science or science-related field, you need to know how, at least some, you need to have some ideas at least how this or that formula can be derived. If you just grab the formula and use it, you don't know the limitations, right? It's not the best situation, right? So you need to have some ideas how this or that can be derived. And this should be derived because this formula is not something fundamental. Pretty much the whole semester, this semester, most of the time we just introduced fundamental equations like Gauss's law, Ampere's law, Faraday's law. As a result, not the result, those laws cannot be derived. As a result, I just usually presented that law to you, and then we learned how to use it. But this stuff is not fundamental. This stuff is derived from those fundamental equations. So it's better, of course, to know how this or that formula can be derived so that you will know the limitations of the formulas. Okay, so now let's get to the geometry. So let's assume that this is our slit number 1 and slit number 2, so double slit experiment. And of course, we must illuminate the system with a laser light, because when we derive those conditions, you remember we use traveling wave equation. Y equals A sine kx minus omega t plus phi 0. We use omega t. Basically, we tacitly assume that our wave has a single frequency, that basically we have a monochromatic source. Because usual light, like if we use this white light, of course it has a wide range of frequencies. It's a broadband source. But in this experiment, we have to use monochromatic source. So laser must be used. Otherwise, we wouldn't be able to see any of these fringes, interference fringes. Okay, so let's assume that we illuminated this structure with the laser light. And let's assume that the distance between slits is d. Usually it's given. If you purchase double slit, usually it's written. So d is 0.4 millimeters or 0.5 millimeters. In the demonstrations which I usually use when we have normal semesters, d is usually 0.4 millimeters. Okay, then of course we need to place a screen where we want to see all that. And let's assume that the distance to the screen is L. And L usually is large. Again, in the demonstration, in the lecture hall, L is usually, I set it to 2.5 meters. So this distance is 0.4 millimeters, basically half a millimeter. And this distance, 2.5 meters. So the difference is gigantic between L and D. Okay? So it's actually a very important point. I will emphasize on that in a few minutes. Okay, so now, let's take a completely arbitrary point on the screen, P, completely arbitrary. And basically, I want to get conditions that I have to match or satisfy in order to get a bright spot at point P. Bright spot, right? Not dark, bright. Okay? So that's my goal. And now let's add some elements to this picture, right? So first of all, let me introduce some auxiliary lines showing the center of the system. Right, you see this line, it shows this is the center of the screen and center of the double slit. Then of course, let's define a position of this point P with the angle. Let's assume that that point P is, can be defined, direction to that point P can be defined by this angle theta. Right? Okay? And again, you remember, we want to get the conditions for a bright spot. And the formula which we derived in our previous recitation class. And we're going to use conditions for constructive interference because, again, we want to get bright spots. So this must be equal to integer number of 2 pi's. All right? Okay, now, next, let's simplify that. Similar to the way we simplified in our first slide. what can you say about the inherent phase difference of wave produced by this slit and wave produced by this slit? These two sources are identical. So the initial phase of this source and of this wave and initial phase of this wave are exactly the same, because basically what is happening over here, we just split this laser light with these two slits. It's basically exactly the same source. So initial phase of both of these waves are exactly the same. So these two sources are identical. So the inherent phase difference is 0. So delta phi naught is 0. Right? Make sense? Of course it should. So now as a result, we can adjust this reasonably complicated condition and replace it with reasonably simple. Again, delta phi is 0, then 2 pi and 2 pi gets cancelled, and as a result, we will have that delta r must be equal to m times lambda. So that's what we have to satisfy in order to get the bright spot at that point P. So now effectively, we just need to do what? We just need to measure delta r, the path length difference. Again, what is the path length difference? Is that additional path length that, for example, this second wave has to cover, again, relative to the first wave on the way to the point in question, on the way to point P. All right? So we just need to draw R2, R1, and see what's the difference between them. That's it. So ideology, very simple. Just a little bit of geometry. We have to get through some geometry. Okay, so now we need to draw, as I said, R2 and R1. So let me draw it. Okay, I will draw this. R1, so this is path length R1 from the first source, and this path length from the second source. Now I pause, because at this moment you should start searching for rotten eggs or rotten tomatoes and start throwing them at the screen, right, trying to reach me, because it looks strange. Because what is R1? For example, R1. R1, it's a distance from the source, here the source, to the point where we want to find the conditions, where we want to, which we discussed. So pretty much from this point to that. So strictly speaking, I should have drawn something like this, the line from this point to this point. And the same R2, it should be from this point to this point. Again, straight lines. Right? Right. But the trouble is that this picture is way out of scale. Way, way out of scale. This distance L, as I already mentioned a few minutes ago, this distance L to the screen is way, way, way larger than this D, distance between the slits. Like I said, this is about like a half a millimeter. This distance is 2.5 meters. It can be 5 meters. It's a gigantic difference. Really big difference. So if, for example, let's say you zoom out this picture and draw more or less in scale, more or less realistic picture, you will see something like this. I took it from the book. Look, all this mass, double slit, is somewhere over there, basically invisible for us. This is L, again, more or less in scale. And as a result, if you draw R1 as it should be from this point to point P, and from this point, from this slit to point P, if you draw it carefully over here, you will never be able to see the difference between this angle, between basically direction of R2 and direction of R1. For you, they will be almost parallel to each other. So with a very, very good approximation, you can treat this way, this path length, okay, this R1, and this as being parallel to each other. That's why I drew this. First seems like a nonsense, right? It's just because it seems like a nonsense because this picture is way out of scale. Make sense? Basically, this is probably the subtle point, right? Okay, so that's why I drew R1 parallel to R2. And as a result, this angle equals to this angle and equals to that angle, because these three lines, this dash line and this, they are parallel to each other, right? Pointing to the point P, right? Make sense? Okay, so now where is the delta R? Again, we still want to find delta R. So this R1 ends here, this R2 ends also here. So where is the path length difference? At the very beginning. At the very beginning. So how can we find it? So if I draw a line perpendicular to R2, you see this line, and this small stretch, this small section, this small length, that's our delta R, this delta R. That's the additional path length that the second wave has to cover on the way to the point P. So basically, we just need to find this distance and equate it to m lambda. Okay, so now look, if this is angle theta, you see it's pretty much all geometry, but we have to be careful with this geometry. So since this is angle theta, what can you say about this angle? This angle complements this angle to 90 degrees. So this angle is 90 minus theta. Then look at this triangle, this point, and this point. It's a right triangle, right triangle. So as a result, if this is 90 minus theta, this is 90 degrees, then this is theta. All right? And now we can finally write down. So let me introduce a few points. This point A, this point B, and this point C. Basically, we're looking at this triangle, A, B, C. And this angle theta. And again, we need to find this side, which is opposite to a given angle theta. So how can we find BC? Piece of cake, right? So we know this hypotenuse, which is D. AB equals D. So D times sine of this angle gives us this distance BC, which is our delta R. Right, so you see delta R equals D sine theta. Okay, now let me show it in this box. So again, as I said, from the triangle ABC, right? So we can get that delta R, path length difference, this delta R equals to D sine theta. And of course, since again, you remember, we want to get conditions so that at this point P, we're going to get constructive interference. So it must be equal to m lambda. And so basically, since we're going to, you see, m is integer. M is integer, 0, 1, 2, 3, 4, 5, all the way to infinity, right? So basically, we're going to have lots of bright spots because of many integers. As a result, it makes sense to put the subscript m next to the angle theta. So as a result, we're going to have theta 0, theta 1, theta 2, theta 3, and so on. So theta 1, for example, gives us an angle to the 0th bright spot. Then theta 1 gives us a direction to the first bright spot. Then theta 2, theta 3, and so on. Right? So basically, that's it. That's what we need. Strictly speaking, this is the condition for a bright spot at point P, to get a bright spot at point P. Right? Okay, yeah, again, you can use it. Nothing wrong with that. And let me, before I continue, these changes. Of course, we're going to see a bunch of bright and dark spots. So bright spot, dark spot, bright spot, dark spot, right? Or I can put a picture like this again. Bright, dark, bright, dark. So first, at the center of the screen, you must have bright spot all the time. You see bright spot. Why? Oh, look, m equals 0. As a result, it gives us the 0th bright spot. When m equals 0, theta equals 0. Theta equals 0, it's the center of the screen. Because you see, we're measuring theta from the center of the screen, from the direction to the center of the screen. Then this will be theta 1, this theta 2, this theta 3, and so on. right? So now, next one. Okay, nothing wrong with this formula. You can use it. But, okay, I work with optical tables, right? So pretty much since I came here, right, my PhD was about optics, right? And I can tell you, if somebody tells me, set up experiment like this, and measure angles, I'm not going to be, I would not be happy. I would be very unhappy, or maybe even worse, all right? Because measuring angles, it's not very pleasant. Of course, most likely I would adjust the work. Most likely I would just try to measure the distance. For example, from the center of the screen to the point where the bright spot is. Because measuring distance on the screen using ruler, what can be easier than that? Grab the ruler, measure the distance, right? Instead of torturing yourself, measuring this angle somehow, plus a light is not visible, right? So you need to find somehow where that light goes, right? So it's not impossible. It's not very pleasant. So it's much better to adjust this equation slightly, right? So that we can measure the distance from the center of the screen to the point where the bright spot is. So that we can replace, instead of dealing with theta, we can deal with y. What is y? You see, I introduce coordinate axis y, pointing upward. And 0 is over here, the origin, y equals 0. So then, as a result, this will be y1, this will be y2, and of course, since this is bright spot number m, so this will be distance y sub m. So I'm kind of running out of space over here, so I open a y sub m over here, right, inside of the picture. So now we just need to calculate this distance ym from the center of the screen to the point of our bright spot. And that's, again, simple geometry. Let me introduce additional point. For example, this point S, right? You see point S. And look at this triangle, S, P, and O. It's a right triangle, you see, because this angle is the 90 degrees. And so we need to find this distance PO, which is ym. In this right triangle, we know this distance L. We need to find this ym, piece of cake. Tangent of this angle theta equals opposite side, ratio of the opposite side to the adjacent side, y sub m divided by L. So from this triangle, as I said, SPO sounds like HBO, right? Okay, whatever. Tangent theta m equals ym over L, right? So this formula allows us to switch from measuring angle to avoid measuring angle, and we can measure angle, and we can measure distance y. So now we can combine this formula with this formula, and basically that's what we need. That's what we need. This you can use to find the angle, and then plug it here to find the distance to the bright spot. So you can predict where the bright spot is going to be on the screen. But we can simplify it even more. That's so nice when you can simplify. Look, okay, not look. Usually, again, as I said, during the normal semesters, I bring these set up, right, and I show usually on the wall these fringes, dark and bright. And you know what? All those fringes are maybe within maybe 1.5 centimeters. All those visible bright fringes, bright and dark spots. And the distance to the screen, okay, to the wall from the double slit, maybe like 2.5 meters. You can imagine, right? So what are the values of these angles? Very small. Very, very small. Probably much smaller than 1 degree. So all these angles, all these theta 1, theta 2, theta, usually you can see like 5, 6 fringes. So all those angles are very small. So if an angle is small, so what can be used? Taylor expansion. You remember at the beginning of the semester, I think the first and the second homework, you use Taylor expansions. So we can use here, with a very good approximation, Taylor expansions. And we can simplify this formula, these formulas, in order to get a single formula. So you remember Taylor expansion, sine of angle theta must be equal to the angle. Angle must be in radians, only true in radians. And tangent of the angle equals to the angle itself. Taylor expansion. As a result, instead of this tangent theta, we can use theta. Instead of sine, again, theta. So now, as a result, theta equals ym over L. From the second equation, theta will be equal, this d goes downstairs, m lambda over d, m lambda over d. Equate them, solve for ym, and that's our final formula, finally. Distance from the center of the screen to the mth bright spot equals integer m, you see 0, 1, 2, and so on, times wavelengths, times length, distance to the screen, and divided by the distance between slits. So that's what we need to use in order to use this, in order to predict, again, the distance or position of the bright spot. Again, that's for bright spots. Right. How can this be used, for example, right? Let's say the wavelengths of the laser is not visible, or is not known. Here you can use this to, for example, measure the wavelengths of the laser. But in a few minutes, okay, maybe in a few minutes, right? I will tell you the sort of problems with this setup. Okay, so anyway, so that's what we need to use, and we're going to practice it next week in problems. Okay, so that this is again m equals 0, bright spot, m equals 0. Then m equals 1, m equals 1. So everything is symmetrical relative to the center of the screen. So m equals 0, then m equals 1, m equals 1. M equals 2, m equals 2, bright spot. M equals 3, m equals 3. So we have complete symmetry, of course, relative to the center. Right, so then, of course, exactly the same can be applied to find position of the dark spots. But of course, you know the dark spots are going to be between two adjacent bright spots. So actually, we barely use this formula, right? But yeah, why not? We can mention it as well. So next, what sometimes is important, and we're going to use it in the problems in our recitation class. Let's calculate the distance between two adjacent bright spots, between any two adjacent bright spots. For example, let's find the distance between bright spot m plus 1 and the bright spot m. So they are adjacent to each other, right? Okay, so we know the formula at the end of the previous slide. So this will be m plus 1 lambda L over d, and this m lambda L over d. Of course, this term m and this term m, they get cancelled. Right? They cancel each other. And as a result, we will have only this 1 times lambda L over d. What's the major feature of this expression? That it doesn't depend on m. It doesn't depend which two adjacent bright spots you're going to use. Maybe 0 and 1, or maybe 1 and 2, or maybe 101 and 102. Distance between any two adjacent bright spots is exactly the same. So all these bright spots are equally spaced. It's important to be aware of that because it can help you to solve problems. In double-slit experiment, all bright spots are equally spaced. Again, sometimes it's very useful to be aware of that. Right? Okay, so and now I just again plotted this. Not plotted, just copied and pasted from the 2 slides ago. We had something like this, but now I just added all these bright spots, dark spots with integers, right? But nothing new. Now, question for you before we go. Very simple, but you need to be aware of this, and I like this question. So let's assume that we have a double slit, right, illuminated by the laser beam, and here the screen. So when 2 slits are open, of course, we are going to see this interference pattern, all these bright and dark spots. Again, at the center, you see the bright spot. Again, they're equally spaced and so on. Right? Now, next, what if I take piece of paper and something else and block one of these slits, only one. The second is open, but this one is blocked. What are we going to see? So first, when two are open, we see this interference pattern. Now, what are we going to see if we block one slit? Every other bright spot disappears. Option A. Why not? Maybe. Since we blocked that side, that slit, all these the bright spots on the left side disappears. Only those appears. Maybe they will just exactly the same distribution of bright spots, but they will get dimmer, or we're going to have just a uniform distribution of light. Okay, I will give you like half a minute. Again, the poll is in the chat. At this point, you're aware. Okay, try to answer it. Okay. So what are the answers? Okay. Okay, so far I like distribution of your answers. Okay, awesome. Okay, I see that you wrote something in the chat. Error. Okay, I cannot tell exactly what can be wrong. Okay, so let me discuss. Okay, I like what I see. Right, distribution again of your answers. Look, we see this interference pattern because of what? Because of interference. Interference are possible only when you have at least two waves. At least two waves. Of course, you can have interference when you have more than two waves, but at least two waves. Yeah, when you have two slits open, of course, you're going to have two circular waves overlapping, interfering, giving this pattern, giving us this pattern. Once you block one wave, one slit, one wave will disappear. As a result, we will have over here only one wave, one circular wave spreading, reaching the screen. One wave cannot interfere with itself. There must be the second wave. As a result, all this nonsense, A, B, C, when I was showing these slides, I could barely hold my smile, right? Because obviously, this is the correct answer, answer D. Because now we will have only one wave, and there is nothing to interfere with, and one wave is going to give us just a uniform distribution of light, right? Okay, so the answer is the correct answer is D. Now, before we go, let me hold you. We still have a minute, and I will hold you for an extra minute. Natural transition. Again, during the regular semesters, right, I demonstrate double-slit experiment. And usually students see that this interference pattern within a very, very short distance, maybe like within a couple of centimeters, all those are bright spots, bright and dark spots. If you want to use this double-slit experiment, for example, to measure the wavelengths, calculate the wavelengths of a laser of some other radiation, it's very, very inconvenient because all those, just a second, guys, all those bright spots are very closely spaced. It's difficult to measure accurately the distance between them. I tried. The experimental error will be large, and your measurements will be basically a piece of junk, almost. Right? But of course, if you don't have anything else, you will be happy with even these results. But so the question is it possible to improve this system? And of course, in which way we can improve it? Can we, for example, spread these bright spots? So instead of like a millimeter distance between bright spots, what about 40 centimeters or maybe 30 centimeters? So we can easily and accurately measure the distance between bright spots in order, for example, to calculate the wavelengths of the laser. Use it as a spectrometer, for example. And the second, can we make these bright spots even brighter? It's a natural desire of anyone who would try to use double-slit experiment, for example, to measure the wavelengths of a radiation of a laser. And how can we do that? How can we achieve these two things? Increase the distance between bright spots and increase the intensity. Look first at the distance between the bright spots in the double slit. You remember, we just measured it, calculated, lambda L over D. So of course, okay, let's assume the laser wavelength is fixed. You can increase, of course, L. But usually, anyone who works in the lab will tell you that it's difficult to get large space. Every time university try to take the space away from you. So it's difficult to make a lab which is very long, right? So increasing L, it's kind of very extensive way of increasing the distance between the bright spot. Not the most efficient way. But if we reduce D, distance between slits, then we will increase distance between the bright spots. And now modern clean room facility in any photonic center can easily, you can easily achieve a distance within a few micrometers. Within a few micrometers, you can get slits easily. It doesn't require significant effort. So if you reduce this distance between slits, you can increase the distance between bright spots, right? Then second, how can we, so that's how we can increase the distance between the bright spots. Then how can we increase the intensity? We did not discuss, but just trust me. So intensity of the bright spots is proportional to number of slits, D it's a number of slits, to the power of 2. So if you have double slit, 2 slits to the power of 2, so the intensity of bright spots is quadrupled relative to the intensity of the incident light. But what if we, for example, create 10 slits? 10 to the power of 2, the intensity will be increased by a factor of 100. But what if you create 1,000 slits? Then intensity, okay, I cannot imagine, right? It will be a significant increase in the intensity. So these are two natural steps that you have to make in order to improve a double-slit experiment. And as a result, you're getting what is called diffraction grating. So in the diffraction grating, you're going to have, okay, let me open it. In a diffraction grating, you're going to have over here thousands of slits. And they're very, very close to each other. The distance between them like a few micrometers. As a result, this device, diffraction spectrometer, is still used in many optical labs to, for example, measure the wavelengths of a laser or some unknown radiation. I used it at some point. So it's just a natural transition from a double-slit experiment to a diffraction grating. Right. Okay, so we will finish this in our recitation classes and we will practice problems. Okay, sorry guys for holding you, but I just wanted to make this natural transition from a double-slit experiment to the diffraction grating. And again, in demonstration, it's very impressive. First, you have all the bright spots are very close. They're barely visible, even for students like in the first row. But once you replace it with the diffraction grating, you have a bright spots equally spaced. No, I mean well spaced, right? With large distance between them, and they're really bright. Okay, guys, thank you, and I'll see you next week.